we working? Okay. So thanks everybody for showing up. And thanks Sally for the topic. Because time is something that we are intimately familiar with, and it's also one of the most mysterious qualities of the universe. And so what I want to do today is I'm going to talk about some of the things that that we know about time and some of the things that we don't know about time, and see if we can explode a few myths. But first, I want everybody to sort of look at this slide here. So you notice that this is from the band Chicago. Some of you probably don't know who this band is because it was a long time ago. But this was a band that was one of the very big musical acts in the 60s, 70s, and 80s. And they had this album came out in 1969. And one of the hits on the album was this song called Does Anybody Really Know What Time It Is? And I thought, wow, that's kind of apropos for the talk. The other interesting thing here is that the band Chicago was actually called the Chicago Transit Authority, but they got sued by the subway system and had to change their name back to Chicago. So why the city of Chicago didn't sue them afterwards, I don't know, but that's another story. The second part of this lyric, however, is the first is, does anybody really know what time it is? And the second part is, does anybody really care? And so I thought that was also apropos for this. And then the third thing you should know is that Sally Ann and I were going to sing this for you. Yeah, but the problem is after we recorded our karaoke, we played it back and we decided to ditch our duet because we didn't want to empty the room right away. So we're not going to do that. So let's start. So what I hope to do is I hope to take you on a little bit of a journey in time, and I have to do it in 10 minutes. So that's the challenge of the task. So we're all familiar with what time means. If I say to you, let's meet at a cafe at 10 a.m., what I'm essentially saying to you is I'm going to give you a set of coordinates, and we're going to meet at that place at a particular time. So it may be that we're going to meet at 199 George Street at Cafe Tiempo, and we know that we're going to meet there at 9 a.m. And that's pretty clear. But it's a set of Cartesian coordinates that we all understand. And we also understand that we attach human emotion to time as well. So for instance, I can reward you, I can discipline you, I can congratulate you on your use of time. If I'm a manufacturing business and I'm putting together widgets and I have components that I need to assemble to make this widget, then I want to have those components arrive just in time. If I am running a project and I want to do a good job, I want to bring it in under time or in time. Or if I don't do a very good job, I can bring it runs overtime. But that's not true for sporting events, because if we're watching the Women's World Cup of Soccer, for instance, we want the result to be tied at the end of the game so that we can watch more overtime. So it depends on how you use the subject. Now, time has been around for a long time. And people have been concerned about time for quite a few years. So this is a site in Peru. It's called Chanquillo. It's about 2,700 years old. It was built in 400 BC. It's 300 meters across. And what it is it's a watch. It's a clock. And essentially what it did was it helped the people who built this 2,700 years ago. It helped them to determine when the sun rises, when it sets, and when certain seasons start. When is the dry season, when is the wet season, etc. And each of these little humps on this particular mountain signifies a specific time of the year. And it's very accurate, by the way. And you see these kinds of monuments to the sun and monuments to the time all over the world. Now, on this slide, you see actually nothing. And this is because This is a particular place in the sky that astronomers have been looking at for thousands of years, and they're not seeing anything. And astronomers were some of the first people in the cosmos who began to think about time. And in this section of the sky, there was really nothing to see. And then sometime in the 80s and 90s, a time machine was put in the sky, and that's the Hubble telescope. And what the Hubble telescope does is it allows us to look at stars and galaxies a long ways away and look back essentially in time. And what we're going to learn in just a moment is that what this telescope sees is it sees light or photons that come from these structures, and we may be looking back very far in time, but the photons themselves don't experience any time at all. So it sort of blows my mind that a photon that left something billions of years ago can hit my eyes and not experience any time, which is very odd to think about, but it's true. So the director of the Hubble telescope has the privilege, a special right, to use the telescope in any way they want for a period of time during the year. And in 2004, the then director, pointed that telescope at this section of the sky, and this is what he saw. 10,000 galaxies showed up because the telescope pointed there for a couple of weeks. In fact, he took more time than he should have. And you'll notice in this particular photo that there are different colors of the galaxy. And the things that are, this is actually a 3D dimensional photograph. And if you, the way to describe this is if you'll see some things that look blue, you'll see some things that look red, and the redder things are further away. In fact, they are about 13.4 billion light years away, or billion years away from where we are, and some of the bluer things are closer. So this is, imagine this in 3D, if you will. You'll also see that there's a little bit of a circular pattern here, and that's due to something called gravitational lensing, which is some of the light is being bent by massive structures that bends around other galaxies and other big things, black holes and things in the universe. Now, one of the things that's important to understand from a contextual point of view is that we are looking, most of the physicists, and Tom will correct me if I'm wrong here, but most physicists think that the universe is about 13.8 billion years old. But that's sort of a really big number, and it's really, really difficult for us to get our heads around how long and how big that is, and how big the universe is, how big space is, how long time is. So to put this in context, I read a book many years ago called Cosmos by Carl Sagan, and he did it brilliantly. He said, let's put the universe on an annual scale. And if we'd say the universe is 1 year old, how long has modern man been on the Earth? And modern man has been on the Earth the last 30 seconds of December 31st of that particular year. So that's kind of mind-blowing. Now, if we've been on the Earth for 30 seconds, think about another civilization who's maybe been around for a minute, or 5 minutes, or an hour. How much more advanced are they? What about a week? Pretty amazing to think about. So we haven't been here very long from a cosmological point of view. So that's the setting. So now how do we think of time? Well, maybe we think of it this way. So if we can imagine that there's a string across the stage from here over to here, and everything happens for all of us at the same time. And if I'm standing here in the middle, I can be the present, and over here are my memories, and over here is the future. So we sort of break it into these discrete units. But that's actually wrong. That's not how time actually works. That's how we might perceive it. And in fact, one of the things that is not obvious at the moment is that you're looking at me in the past. Because what's happening is the photons that are reflecting my image to you are taking a few nanoseconds to get to you. You then have to process this in your brain, which takes a couple of milliseconds. The sound takes even longer. And so you're actually seeing me in the past, and I'm seeing you in the past. So what is now? Don't know. In 1905, this guy came along. And this was a paper by Albert Einstein called On the Electrodynamics of Moving Bodies. And it's more commonly known as the special theory of relativity. What does that mean? That means that it's a special case of what's called general relativity. Now, we won't go into all of the things about this, but we will discuss a few important points. So, in this paper, Einstein came up with this idea that space and time are one thing. Prior to that, in Newtonian physics, Newton said space is one thing, time is another thing, and that's how we thought of it. But Einstein said, no, that's actually not correct. Actually, space and time are one entity. They're one mixed up sort of universal thing. And this leads to a number of interesting conclusions. One of which is time runs differently for different people, depending upon where you are and what you're observing, what your speed is, and how close you are to a massive object or not closer. So, to illustrate this, let's use this example. I have a watch, and my watch says 12:40, which means I have 5 minutes left, so I better hurry up. And lots of people down here have watches as well. And then the gentleman up on the balcony also has a watch. Now, if we let time run for a while, and I look at my watch in about 5 minutes, it'll say 12:45, and your watches will say 12:45, and his watch will say 12:45. But the problem with that is that our clocks are not very accurate. These are actually pretty crappy. But if we had really, really accurate clocks, what we would see is that the clocks run differently. So my clock would run faster than these clocks down here, and my clock would run slower than his clock up there. So why is that? Well, the reason is that you're closer to the mass of the Earth than I am, and I'm closer than he is. And part of Einstein's theory of relativity shows that mass affects how time runs, and so the closer you are to a mass, the slower the time is going to run. So then if we say, okay, what does now mean? And I ask my sister, I say, so what are you doing now? But she lives in Jupiter. So she's living next to a planet, or on a spacecraft outside of a planet that has much more mass than the Earth does. And when I ask her, what are you doing now? It takes some time for that communication to get to her. So what she's doing now, where her clock runs slower than mine, makes no sense. It's sort of impossible. What is now? I don't know what now is. But it's different for all of us. The second thing in this paper that Einstein pointed out is that the faster you go, the slower the time goes. And part of that is due to the fact that the speed of light is always constant. It's invariant. So what does this mean? So this means the following. If we're on a train and traveling at 100 kilometers an hour, and I have a basketball in front of the train and I throw it out at 10 kilometers an hour, the speed of the basketball before it hits the air resistance is 100 plus 10. It's 110 kilometers per hour. Similarly, if I'm on the back of the train and I toss it off the back at 10 kilometers per hour, then the speed of the basketball is 90 kilometers per hour. This is not true for light. So if I'm on a rocket and I'm going at 90% the speed of light and I shine a torch ahead, you would think there would be the speed of light plus 90% of the speed of light, so it'd be 1 plus 0.9, so it'd be 1.9 the speed of light, but that's not the case. It's always the same. It's 1. Similarly, if I shine the light off the back, it's always 1. So the speed of light is always invariant. It never changes. So how does this work? So what this means is that if I am an observer looking at something and something passes by me very, very quickly, that my clock will read one thing and the person or the clock passing by me will read something else. In fact, it will be slower. And so maybe if I can illustrate, or at least try to illustrate how that might work, let's use your imaginations for a second. So suppose I'm standing here and I have a mirror in front of me, and then there's another mirror right here that's reflecting back at me. And if I shine a torch or send a photon to that particular mirror, and let's say it's 2 meters away, it will go tick, tock, and that's my light clock. And it takes that amount of time, that unit of time is what I see. Now, and what you see is you see the same thing. You see tick, tock. Now let's suppose I'm on a Moto Guzzi motorcycle, which is the best motorcycle in the world, and if you've never ridden a Moto Guzzi, then you don't know that, but just take my word for it. Let's suppose this Moto Guzzi motorcycle has Tom Stace has invented a light engine, and that light engine can power this motorcycle at about half the speed of light. Well, if the mirrors are here and I'm going half the speed of light, and I get to here, still for me, I'm seeing the mirror in front of me. But what you see is different. What you're seeing tick, tock, tick. So what do you notice here? The distance from here to here is 2 meters up, 2 meters back. The distance from here to here to here is longer. So something has to change, and that is my clock runs slower. So let's talk about why this is important, and I'll wrap this up in just a minute. So and this is called time dilation. So we have special relativity in our pockets, and it's this thing right here. And on this we have Google Maps, and remember that time runs slower close to a mass, and it also runs faster on a moving object. And so if I want to make sure that I'm in the right place in Google Maps, then special relativity has to be taken into account. And so what that means essentially is that those satellites that are 20,000 kilometers in the air and traveling at 14,000 kilometers an hour, their clocks are different from the clock on the ground, which leads to position. And that means if we don't synchronize these clocks, I can end up up to 11 kilometers different from where I see on the map. And this shows that I'm landing in the plane in North Sydney versus at the airport, which we don't want to do. So what does this all have to do with startups and with the kinds of companies being built? Well, we each have 1,000 minutes a day, roughly, to do things. Frequently, the value proposition of any startup is, how can I do things faster? How can I do things better, more efficiently? And I think what you're going to see in this panel is you're going to see that demonstrated very, very well. So Tom Stace in analog quantum circuits, so he's building circuitry that sits on a quantum chip, which enables the operations of a quantum computer to happen faster and more efficiently without having a whole bunch of wires run in from the outside. And Tom will tell us how help build a 1 million logical qubit quantum computer, which will allow us to build the light engine. That gets us to space quicker. We have Mark Waller, who has a machine learning system that helps chemists build coordinates or build ways to make molecules much, much faster. We have Cicada, who is building 5G and 6G chips, which enables communications to happen faster, and that all requires syncing inside big data centers and networks. And then we also have a company that essentially prints at very high speed circuits, and all of these things are dependent on time. So what I would ask you to do is think about the 1,000 minutes you have each day, think about how time is different for everybody, and use your time efficiently. And now my time is up, so thank you very much.
Thank you so much.